And we are recording. By the way, I'm sorry for the recording mishap on Wednesday. I never know when. It looks like it's recording, right? Best I can tell. The audio on Wednesday's recording was just, I would say it wasn't nothing, but it was just this repeated rattling sound and no human voices at all. It was completely useless. It's happened before. I don't know what the problem was. The next day, it was recording fine. So I hope we're good here. I can only hope. Okay. All right. Oh, and then let me also just as a double check. So I sent y'all an announcement yesterday, I believe it was. I did finally create the Gradescope site for the homeworks. Hope you all got some sort of automated email from Gradescope. So make sure you have that, linked or whatever. And of course I sent an announcement. There were a few other, I walked through the, homework one, just to make sure everybody's on board with what the procedures are there. Okay. Back into the math. Okay, so last time we talked about this idea of geometric order of a list. When you have two vectors in R2, I hope I was persuasive that we can not only reasonably but naturally define these, three concepts. That list is either counterclockwise, clockwise, or dependent. And then, pretty quickly, near the end, but we talked through a sort of a three-dimensional version of this. If you have not two vectors in R2, but if you have three vectors in R3, right, then there is a different way that you can... it's geometric, and every list is one of these three, and two of them are sort of opposites of each other. It's got some of the earmarks of clockwise, counterclockwise. Right? So you might say it's a kind of a three-dimensional version of clockwise, counterclockwise. And then, not only is it vaguely reminiscent, it has all of the same properties of their mirror images of each other. You trade any two vectors and it changes the list order, and the whole thing is independent of rotations. So I think that's really interesting. I will point out there is a I'm going to call this a fourth property. It's not really. This is arguably just a different version of one of the earlier properties. But if you cycle the list, that preserves the order. And here's what I mean by that. Cycling means I'm going to take. See, which way did I go? Yeah, okay, so I'm going to take that vector and put it there. And then I'm going to take that vector and put it there. And then I'm going to take that vector and, oh, no, we fall off. And then you come back around and put it over at the beginning. Right? So, kind of rotating through, as it were, the list to produce a new list. Preserves the order. And what you can persuade yourself is that cycling is in fact just two switches. It's two transpositions, and so you might say that it switches the order twice, aka it preserves the order. Right? Okay, alrighty. Okay, now changing gears. We're going to go back to linear algebra. Y'all may have seen the following theorems in linear algebra. You probably saw some version or, maybe parts of these theorems. Before I get into the statement of this first theorem, I'm going to do some setup. We kind of have to do some setup. If you have a list of two vectors in R2, I will make the observation that from that list you can naturally, canonically, produce a matrix. Right? First vector, first column, second vector, second column. So I don't want to say they're the same thing. They're not the same thing. But if you have a list, then you very naturally have an associated matrix. Which, by the way, per the usual construction, means that you have an associated linear transformation. Right? Now this is getting a little weird at this point. We have three different mathematical critters. A list, not the same as a matrix. Not really technically quite the same as a linear transformation. Of course, they're very, very naturally related. They're so related, we often blur the distinction. Technically, they're different. Right? One's a function. One's an array of numbers. And then I will point out that not only can you construct a matrix and a linear transformation, you can also construct a corresponding parallelogram. And you can think of this parallelogram two different ways. You can think of it as that first vector that made the first column becomes the first edge, and the second vector that becomes the second column, you make the second edge. That's one way to think about it. Another perfectly valid way to think about it is that this is what results when you take the unit square and plug it into that linear transformation that you've already constructed. Right? So this parallelogram is the image of the unit square by way of the transformation that comes from the matrix, that came from the list. All right, so lots of setup. I haven't done anything yet. I haven't made any statements. I'm just saying, hey, I choose to do the following, and I just made a bunch of stuff. Everybody on board so far? Yes.
How do you, what is S?
The unit square. So the unit square means it's the square in the xy plane where sort of the x interval is 0 to 1 and the y interval is 0 to 1. Okay. Yeah. Usually commonly called the unit square. Yeah. Okay. So now let's actually look at some statements. All of this setup having been made. And I am going to go full screen, give myself a little more space on the board. First, wacky statement. Shocking statement. The determinant, okay, technically, the absolute value of the determinant of that matrix will give you, let's see, color choices, dark blue, will give you the area of that parallelogram. And I think this is a really surprising fact. Determinant is 3-function arithmetic. It's not even, no division even, right? This is add, subtract, multiply. Really basic arithmetic, right? Area, heretofore, case could be made that the way you would think of computing this area is by dropping a perpendicular, let's see, let me write it on the screen here. Dropping a perpendicular kind of like this, and thinking about this distance here. So you're going to have to compute a magnitude. That involves a square root. Ugh, that's ugly arithmetic. Computing this, you would use probably trig, ugly arithmetic. And by relating it to this side length, which again, a square root, right? So super ugly arithmetic on the right, trivial arithmetic on the left, right? Our natural sort of built-in, nonsense detectors are beeping. Hey, wait a second, this couldn't possibly be true. Simple stuff can't equal the hard stuff. But it's true. It's shocking how this works out. Really, really surprising fact. So anyway, cool stuff. Dig it. Here's the next cool fact. The sign of the determinant. Just the plus or minus. The sign of that determinant tells you about the order of the list. Let's see here. I guess I will use purple. The order of that original list. Is that list clockwise or counterclockwise? So again, pretty surprising. I mean, we've thought of the idea of the order of a list as being, again, this extremely geometric idea of which way do you turn, and stuff like that. And it boils down to a very simple interpretation from a very simple computation of trivial arithmetic. So again, I think it's a really surprising fact. Did you have a question?
I was just wondering what you meant by, you might not have gotten to it yet. Please.
Oh, okay, yeah. No, I think I know what you're asking about. I will get to it. Yeah. Okay, so really surprising, So in particular, and now I'm going to have to zoom out to fit all this in. So positive determinant. So when that is positive, what it means is that the list is counterclockwise. And this drawing that I have right now is an example of that case. I got my colors different, but anyway, this list being counterclockwise because A first, B second, counterclockwise. And so I claim if, in fact, the A and B vectors are what I have drawn here, if you were to produce this matrix, if you were to compute its determinant, it would be positive. And I can tell that just because this is counterclockwise. So pretty wild. Now, I do want to represent what it looks like when it goes the other way. And unfortunately, I can't... I mean, when I draw, I can only draw one or the other. I chose to draw this as clockwise arbitrarily, but let's suppose that I have the A and the B different. So I'm going to erase that, and now let's suppose that that's A and that that's B. Right now, let's see here. The list is clockwise, and again, if you were to take those vectors and assemble them into a matrix in the way I've described there, that determinant of that resulting matrix would be negative. That's the other possibility. Well, this third possibility is that the determinant is 0, and I think y'all's memories of linear algebra can probably persuade you that means the AB list would have to be dependent. Let's think about what you already know from linear algebra. Okay, so there's another way to think about this, what we're looking at here. So the way I've got the current scenario drawn, the list AB is clockwise. Now I want to think through some geometric, let's just connect a couple of dots. Looking at that clockwise list. A first, B second, clockwise. Now wait a minute here. The first vector being A, that corresponding to the first column, that being therefore the image of the first standard basis vector. Y'all remember that one? We're going to talk about this briefly later today. But when you have a matrix interpreted as linear transformation, the columns are the images of the standard basis vector. They're the images of I, J, K. In this case, I and J. Okay. So this green vector goes to that green vector. The second vector, B, well, that's the second column, which means that B is the image of the second standard basis vector. And now, wait a minute. Well, let's interpret from this picture what just happened here. This green and this blue went to that green and that blue. What can I do to space over here? Well, it looks like I'm going to have to kind of stretch it out that way, and maybe there's a little bit of a rotation or whatever. But you know what is absolutely going to have to happen? No way around it. There's going to have to be a flip of some sort. And the reason I know is because the standard basis vectors in the usual order are always counterclockwise. I to J, E1 to E2, always counterclockwise. So a counterclockwise list of vectors has images that became clockwise. How do you turn counterclockwise into clockwise? Well, not with stretching, right? Not with shearing and not with rotating. None of that will change the order. Flips, turning it upside down, right? What I'm going to loosely call inverting has to happen for that to be possible. So this is the other translation that I'm going to make. Right, the other interpretation, if the determinant is negative, aka your list is clockwise, another way to say that is that your linear transformation inverts the plane. It flips it over, flips it upside down. Is that cool? Is everybody on board? Yes.
So it always has to be counterclockwise?
The standard basis vector is just straight up R, always counterclockwise. Yeah, absolutely. Yeah. And the question is, are the images, the one or the other? Okay. All right. So I think that's a really nice interpretation. By the way, there are different times when different of these interpretations are useful. Sometimes you want to know whether the list is clockwise or counterclockwise. Sweet. Sometimes it's just not what you're interested in. Sometimes you need to understand the linear transformation. What is this linear transformation doing? Right? And being able to reinterpret a statement about lists into a statement about how the linear transformation works. This is a valuable reinterpretation. Okay. There's a three-dimensional version of this theorem, and it's exactly what you think. I deliberately wrote this theorem on the page. Look how it sort of lays out on the page, right? I wrote it to lay out on the page exactly like the previous theorem. I want it to look the same because it is oh my God, it's so the same, right? So this analogy is not only valid, but I think valuable, right? What you understand about what we just did will help you understand what we're about to do. In fact, I'm just going to mostly kind of wave my hands on it, at it. If you have a list that makes a matrix, that makes a transformation, that makes kind of a three-dimensional version now of a parallelogram. This is called a parallelepiped. It's a three-dimensional parallelogram. And again, the results are exactly what you think. The absolute value of the determinant tells you how big that thing is. Well, it's three-dimensional. Of course, that means volume, not area. And the sign of the determinant tells you the order. It's not clockwise, counterclockwise at this point. It's the three-dimensional equivalent, right hand or left hand. But again, it tells you about the order of the list, and likewise, it tells you whether that transformation. Oh gosh, now we have a language kind of challenge. I like the word inverts in the sense that let's go back to 2 dimensions real quick, right? There's a lot of ways to think of the plane inverting. You can think of it as flipping it upside down. You can think of it as a mirror image. And you have options. It's a little harder to understand the idea of flipping something over when it's already three-dimensional. You got to flip through the 4th dimension? Well, yes, by the way. That is a way to think about it, but it's a pretty intimidating way to think about it. And good news, you don't have to. Easier is to just think of it as, well, it's equivalent to a reflection. Reflecting through a plane of some sort. But just to avoid, sticking ourselves to one interpretation, I still like this word inverts. So you interpret that however you like. Okay, so neat result. I'm not going to prove this theorem. There's a couple of ways to prove it that I'm aware of. The way, if I remember correctly, the way the book does it, and the way most books do it, involves lots and lots of what I'll call drudgery. Right? It's trig and algebra just explode, and then you wade through all this massive work, and then you get down, and sure enough, it works. There's a much better way to prove this, in my opinion. It uses linear algebra. A little bit sophisticated linear algebra. It would take us most of a class period to go through that linear algebra. This isn't a linear algebra course. That it's not a good use of class time. But I figured, why go through drudgery when it's not even the best way to think about that result, right? What's the point of that? So I don't want to direct you toward ideas that are ultimately unnecessary and painful. There is a better way to think about it. By the way, if you're curious and you want to hear sort of the broad strokes of this better way to prove this result, come on into office hours. I'll be happy to walk you through the big ideas, and you can think through the details for yourself if you like. You do not have to. You're not responsible for the proof of this theorem. You are responsible for knowing the theorem itself, though, and understanding what the theorem's saying. Okay, all right. So let's see. So we talked about order. We talked about determinant. And there's a third player in this conversation that is a large part of why we're here. Yeah.
Just before, when the determinant is 0, is the cube switched to a plane or a line?
It could be either, right? So the linear algebra version of the answer is that this third case, the matrix in question is not maximal rank. So the rank is not 3. It could be 2, in which case the image is a plane. Right? It could be 1, in which case the image is a line. And it could be 0, in which case the image is a point, just the origin. Right? So either of those is possible. And the classifying and getting inside of that category and further classifying doesn't really benefit what we're doing in this class. So, but yeah, there are distinctions in there. Okay, so the third player, the third sort of curiously connected mathematical operation that we need to understand, this idea called cross product. And how you motivate cross product is reasonable people disagree on the best way to do this. I'm going to do it in a way that's pretty different from what the book does. We're going to have all the same results, right? But there is no undisputable best way to do this. Every way to do this has some disadvantages. And I'm going to confess the disadvantage to my approach right off the bat here. I'm going to write something down with no motivation at all. Right? And the motivation, I'm sorry, but you're going to have to wait. The motivation will come later this lecture. But here's a formula that I'm going to write down for no apparent reason. That formula right there. This is the formula for the cross product. And you should be mystified right now as to why I would write such a thing down. Okay. All right. Now, several things to say. First of all, in my life, I have never memorized this formula. I've used cross product a million times. Never wrote down this formula. Only the once to write it down in the notes. Right? But I've certainly never memorized that formula. I think it's much easier to just remember this, what I'm going to call symbolic determinant. I have to say symbolic determinant. Symbolic because it's not really technically, I'll say this, our understanding of what a matrix is, this is not that. Heretofore, I'll bet you every matrix you've ever seen, the elements of the matrix were numbers. I've got a few elements of this matrix that are vectors. That's unprecedented in your experience, almost certainly. So, since this is not something we're accustomed to, I'm doing a familiar operation to something that is not the familiar target of that operation. This seems highly suspicious, and sure, it's a little suspicious. But if you proceed anyway, looking just at the symbols, just write down determinant in the usual way and interpret in the only way that seems to make sense. It turns out that, yeah, sure enough, there you go. Right, yes?
Is the reason that the second entry isn't written as A3B1 minus A1B3 because it's easier to correlate to the determinant?
Yep. Oh, yeah. No, you point out very correctly that this minus sign easily could have distributed. It would have amounted to basically switching the order of those two times. And it would be simpler looking but harder to relate to that claim. Absolutely. Yeah. Okay, so check that for yourselves. By the way, don't forget what these vectors are. This E1, it's just the first standard basis vector. 1, 0, 0. It's what a lot of people like to call I hat. I don't like that IJK notation because it's very limiting. It's very constraining. Unless you're going to do IJK, LMNOP, QR, ST, right? If you're working in 11 dimensions and you need 11 standard basis vectors, I mean, that's what the IJK pattern would yield, right? It's just so much easier to call them E1, E2, E3. And if you need more, okay, E4, E5, E6, E7, E8, right? Pattern's easy. Personal preference. Anyway, be aware what these are. And again, confirm for yourselves that works out. You got to write some things down, right? But it's a good exercise. Okay. So that noted, here's a few other observations. This next one is hard to see coming, but once you see it, it's pretty straightforward. If you take a dot product of the cross product with some other, and here it is, by the way, there's that cross product, and you cross it with some other vector, like C1, C2, C3. You could write that down, and you could multiply it out, I suppose, but you could also cleverly observe that this thing, whoops, wrong color, this thing that you get when you dot is in fact a straight up, no asterisk, good old fashioned determinant. So that's pretty weird. Yeah, no, this is not symbolic. Everything in here is a number, so this is just plain old determinant. Okay, yeah.
Sorry. What does the matrix with the unit vectors look like? Like, is it like, do you add them into the column, or is it like a 5 by 3? Like,
no. It's E1 is the top left element, and look, you're unhappy with my suggestion, as you should be, right? But yeah, no, this does not change the shape of the matrix. This just makes it not a regular old matrix as we've previously been familiar with. And so, yeah, it's kind of nonsense. And you can't do with it the things that you do with most matrices. It's a bunch of, like, what if I made one of the elements, Tuesday? What are you talking about? That's not a thing, right? So, likewise, you should be uncomfortable with this, but just ignore that discomfort, compute and determine the usual way. Okay, so it turns out this fact that we just wrote down here, by the way, this construction here is called the triple product. Let me do it like this. This construction is called the triple product, and this formula is called the triple product formula. Super useful. Really useful, and broad strokes, and there's sort of just a plausibility check on my claim that this is useful, this is a connection between determinant, which I'm going to say we understand pretty well. We have a lot of knowledge about determinant and how determinant works. Right? We're strong on determinant. We're strong on dot products. Right? So if I have a formula that relates those things that I understand to this new construction called cross product that I wish I understood better, being able to relate what I want to things that I already know is a good foot in the door, right? That's ultimately why I think why this formula is so valuable. Okay. All right. Okay, so off we go. We're going to see a bunch of cool stuff about cross products. By the way, I'm sad about this, but I did have to accept the difficult choice that these beautiful arguments that I really like and that I think are super instructive. It's really good sort of brain exercise to think through these arguments. But golly, given the goals of the course, given the limited time, tough choices, and all that, I don't think I can justify going through them, and they're sufficiently non-trivial that I therefore think I can't even hold you responsible for them. So you don't have to know these proofs. The ones that say optional, right? You're not responsible for them. These proofs will not be on the test. Now, these facts, 100% definitely fair game. You are responsible for the facts themselves, right? But these super cool proofs, technically not responsible for. Now that said, I would encourage, if you're in the market for practice and you want to work yourself out and get a good bit of mathematical exercise, right, to strengthen your understanding of cross product, I think these are fabulous, and I encourage you to walk through and think through these results. But again, it is optional; you don't have to do it. Okay, so let's talk through the facts. The cross product has this wonderful feature that it's always orthogonal to both of the input vectors. You give me any two vectors, you cross them, always orthogonal. And, not hard to prove. Y'all know how to prove orthogonality. Orthogonality means the dot product is 0. So, take these dot products, compute them out, and just show that they indeed give you 0. Right? That's all there is to it. Very doable. But there's also this really clever proof that uses the triple product formula. I encourage you to take a look, but you don't have to. Anyway, true fact, always orthogonal. Next weird true fact, the triple product cycles. Now, at a quick glance, you might look at this and think that it's like, isn't that like an associativity or something? It kind of, at a quick glance, sort of looks like an associativity. It's not, right? This is weird. This is super weird. One of the vectors here that was a participant in the cross product over here, it is not a participant in the cross product, right? That's some strange remanipulation there. But you'll notice we're cycling through the lists of vectors, as it were, in terms of writing them down that way. And the way you prove this, again, you don't have to know this, but triple products are determinants, and we know determinants are preserved by cycling columns, and therefore triple products are preserved by cycling the players. Yes?
So order matters in a cross product?
Yes, absolutely. Very much so. Yeah. We'll get to that as well. Absolutely. Yeah. But if you cycle the triple product, nothing changes. Really cool fact. By the way, technically, I will acknowledge that this could be rewritten as A cross B dot C. Dot products are symmetric, so sure, you can totally do that, right? Please don't. You're just going to create confusion, right? Because it seems to have changed the order of the vectors in the list, and you're just creating confusion. This is legal, but it also buys you nothing other than trouble. So please don't go out there and get a real good deal on free trouble, right? I don't think that's a good investment. So, so I discourage that. Okay. Here's a really mysterious, weird one. If you have two vectors, A and B, and if you look at the cross product of those two vectors, and more to the point, if you look at the magnitude of that cross product, that magnitude mysteriously, at least at first glance, gives you the area of the parallelogram that the original two vectors define. So again, super weird, right? I mean, think about, so cross product is defined with formula. The formula was motivated by algebra. Again, this is what I'm going to call a largely algebraic left-hand side, and on the right side, all geometry. So very strange, very hard to see this coming, but true fact, very useful true fact. Yeah.
What do the two lines that are only on the left side of the
Thank you.
parentheses?
Yeah. That's another notation that I have to elaborate on. This thing here in orange, that's just notation to represent a parallelogram. It's this parallelogram right down here, the parallelogram defined by these two vectors. And I am not sure if I subconsciously remembered seeing this formula somewhere before, or if I made it up. I'm just not sure. But either way, I think it's a really natural and simple notation to use parallel lines to define a parallelogram, right? And then likewise, you'll notice I use a similar notation down here. Here I have a parallel with three things following. That refers to the parallelepiped. Yeah. Thanks for the question. That was a good question. Yeah. So good generic, convenient notation. Yeah. Okay. So again, really cool proof. I hope you'll take a look. You don't have to. By the way, I do want to point out if you do look through this proof, you might think to yourself the same sort of thing that I thought to myself several times when I was in y'all's position, which is, oh my God, I never would have thought of that. Oh, where did that come from? It comes out of nowhere. Why are we looking at this construction? Why the determinant of that? Where did that come from? It comes out of thin air. I never would have thought of that. Right. Absolutely. I didn't think of that either. Somebody showed me this cool trick when I was about y'all's age. And a lot of that math, that, one person who spends their lives thinking about things and just, gets lucky and finds this amazing, clever trick. And then it spreads like wildfire, right? And that's as it should be, right? So anyway, please don't make the mistake. I made this mistake when I was y'all's age. I encountered, it wasn't this specifically, but something super clever like this. And I just thought, oh my God, I never would have thought of that in a million years. I guess I'm not very good at math. I had that thought. Right? And wrong. It's not reasonable to expect yourself to have been able to have thought up every super insightful, trick that anyone's ever thought of. So please don't make that mistake. Okay, here's a cool one. Cross product. When it's 0, tells you the list is linearly dependent. I like to think of this as being sort of a complementary idea to this, a similar fact with dot products. When the dot product is 0, the vectors are perpendicular, orthogonal, right? The 0 thing is super annoying. Dot product being 0 for non-zero vectors, perpendicular. Cross product being 0 for non-zero vectors, again annoying, means parallel. So dot product, cross product. What happens when they're 0 are sort of opposites of each other. So that's kind of cool. Again, clever argument with the proof. Here's another neat fact. Very cool. This list, if you have two vectors, A and B, and then you cross them, and very importantly, you cross them in the same order. First vector on the left, second vector on the right. So first vector, second vector, cross product is never in left-hand order. Usually that list is in right-hand order. Obviously we have to make the distinction. Sometimes one of the vectors is 0 or annoying. So usually, other than zeros, that list is in right-hand order. That's another really cool fact. It's intrinsic to the cross-product construction, worth mentioning. And again, super cool proof, easy and super cool proof. Give it a look. Okay. All right. So here we have now gotten to what the book uses as a definition of the cross product. And as I mentioned, I was going to do something very, very different. I like the development that I give because the development I give allows for some very geometric, conceptual-based arguments that prove all of the results except for one, tedious matter at the beginning that I sweep under the rug. But it's very geometry heavy, it's very intuition heavy, and I think that's awesome. That's why I like doing it this way. The book sort of does the opposite. The book starts with this as the definition, that the cross product is the unique vector that satisfies these three properties that we've already talked about. It's the only one. There will always be exactly one vector that has these three properties. Think that through for yourself. Persuade yourself that's true. That unique vector that always exists, the book says, let's define that to be the cross product. And what I don't like about this, for one thing, the computations that follow are tedious. That's no fun, right? Tedium is what I like to think of as being as kind of a necessary evil. Sometimes you have to do it, but it's not instructive, right? I like it when there's I see now, right? That I see usually comes from different kinds of arguments, and tedium doesn't. To me, tedium is valid and important and hard to argue with, but it's pretty opaque and unsatisfying. Okay. Anyway, so for your consideration, that's how the book starts off, and then gives very different arguments. Somebody asked earlier about commutativity. Correct. Cross product is not commutative, but it's like super not commutative. It's the exact opposite of commutative. It's the negative of commutative. And weird little situation that when things become sufficiently opposite as to be as opposite as possible, you actually get useful meaning again, right? You cover so not being commutative is bad, but being anti-commutative is actually useful information, right? This is valuable knowledge. So neat fact. And again, clever argument, and you're welcome, but not required to look at that. Okay, a couple of facts that are not in the book that I think really need to get said. For one thing, loosely speaking, cross products are linear. Now I say loosely speaking. What I just said is sloppy. If I were to say cross products are linear and try to defend that statement specifically and exactly as stated, well, that's technically not true. When people say cross products are linear, what they mean is that if you look at this cross product and if you then fix the vector on the left and interpret cross product with this fixed constant vector A on the left, think of that as a linear transformation. I should say, think of that as a function. You give me an x, that's what I'm going to do to x. That function is linear. Is that cool? And by the way, you can see that in this formula. Now, you may have seen this formula at some point. It looks like boring, sort of like, ho-hum properties of algebra. Didn't we establish this back in elementary school? Isn't that just distributivity and associativity together? Well, not really, because this is a statement about a new operation that does not get discussed in elementary school, right? So this fact looks like something discussed in elementary school, but it's not, right? So what this is, again, cross product with A on the left being thought of as a function, what we have here is T of a linear combination being a linear combination of T's, and that is linearity. Everybody on board with that? So, sloppy language, but very convenient, very common. You're going to hear that a lot. Cross products are linear. This is what they mean. Okay. All right. Okay. And then last one. And by the way, on either side. You can do it on the right, and it works on the right too. Yes.
How come in that case it would be T of A?
So this thing, crossing with A, is the definition of what T is. What T does is it acts on some vector to produce an output, and whatever that vector is, that's the thing you cross with A. So,
the second one.
Mm-hmm.
Why would it be T of A?
Oh, because here, T is defined as cross product with A, the fixed vector A on the right, and what this T does to some vector X is it puts that X on the left. Yeah. These are different functions. Yeah. Right. Okay. Lastly, not associative. It's also not anti-associative. It's not anything associative. It's just not associative. Right. So these two expressions they're just different. End of story. There's nothing particularly convenient we can say about that. Okay. All right, real quick, we're going to talk through some applications. When you make up new mathematical constructions, very often people want to know, why do I need to know this, right? So there's a couple of different answers. One reason you need to know it is because hopefully you trust me a little bit. I claim cross product's gonna pull its weight. It's gonna earn its keep, right? Later. So if you trust me, then that's a good reason why. And by the way, a lot of math is that way. A lot of math is stuff that has to get done because there's several things together that have to be done before you can get to an application that uses all of it. Right? So there's that. But conveniently, I can point to some immediate applications. So there's this idea of torque, which is kind of like an angular version of force. Right? Force says how hard are you pushing. Torque says how hard are you turning. Does that make sense to everybody? Okay. It turns out that it's pretty naturally understood with a cross product. So this is a useful fact. Convenient. And again, very natural. Here's another, again, I didn't make it this way. This is the world came to us pre-made to have the following weird feature. But this is how magnetic fields and subsequent forces work. It's surprising. But again, the world was made this way, independent of our preferences. If you have a particle that's moving with a velocity through a magnetic field, and let's say that the magnetic field is that way, and you want to know what is the resulting force that the magnetic field applies to that particle, well, here's the formula. The force is computed as a cross product. Pretty wild. So this is physically natural in these two senses, and again, I cannot emphasize enough, this is not why you need to know cross product. Most of the reason you need to know cross product is because of stuff that we're going to do throughout this course, largely at the end of the course, but it's going to be one of our necessary tools. Okay. Last thing I'm going to say, and again, this is mostly for y'all to read. There is a closely related, different construction called the wedge product. The wedge product, super important at really high levels. As we're going to discuss it here, as an operation on actual vectors, only works in 2 dimensions. But this 2D wedge product, defined like so, tempting to say it's the determinant. It's just the determinant. Technically, it's not determinant. Determinant is something you do to a matrix. A wedge product is something you do to a pair of vectors, right? So, but if you take that list of vectors and you make it into a matrix in the usual way, blah blah blah. So it corresponds to determinant. Anyway, thought as an operation on vectors, it's kind of like triple product in certain ways. The sign tells you the order, the magnitude gives you the area, and it's also kind of like cross product in some ways. because the absolute value gives you the area, and the wedge product is also anti-commutative. So kind of wild. Anyway, there are some small advantages to this construction that come up in chapter 6 and 7. We'll get to that much later in the course. And sadly, it looks like I am out of time. So anyway, we finished 1.4. That's just what it is. Okay, see y'all later. Have a good one. Yeah, give me 2 seconds. Let me just get this stopped.